Good afternoon. Thanks for joining me today. So today I'm going to talk about Kubernetes and get you excited about some of the amazing features of Kubernetes and microservices and how you can actually get your application up and running quickly using Kubernetes. Raise your hand if you're already familiar with Kubernetes. Perfect. And those who are here to actually take advantage of Kubernetes for their AI application or ML, whatever have you? No? Okay. Because this session was advertised within the ML track, so I thought maybe some of you are actually interested to know how you can add machine learning to your web application using Kubernetes and obviously cloud-native microservices architecture. Anyhow, my name is Haghighi. I'm a distinguished engineer at Discover Financial Services. And again, it's absolutely inspiring to see so many developers and technologies coming to Atlanta every year. This is my favorite event of the year, honestly. It's just like the sort of passion you get out of Devnexus is just amazing. And for the past few years, it's just my favorite event of the year. So the sort of topics I'm going to cover today, So I'm going to start with a little bit of background around microservices architecture and containerization, and then I'll basically delve into orchestration using Kubernetes. And then obviously, to take advantage of Kubernetes fully, you need to be aware of operators, custom resources, and all those things that I think not many developers are actually taking advantage of operators now. So I'll be talking about those, and then a quick background on observability and monitoring, and hopefully you get full information about the microservices architecture all the way to deploying and managing your applications with Kubernetes. So this is the sort of intention to kind of give you full background and information around the technology. So to give you a little bit of background about what I'm going to talk about today and why you need to actually have microservices and containerization, I'm going to talk about an application that I built back in 2020. So I was kind of, when the whole pandemic was on the way, I wanted to actually have a display at home to show me all the information about the mortality and the infection rate of COVID-19. And I was always trying to kind of, find a way to have that displaying kind of, seamlessly, rather than kind of, trying to look it up online or trying to kind of show a web page. So what I did was I built an application that captured data from Johns Hopkins University, a repo on GitHub. And then I parsed the data using another service and then tried to have that sort of analyzer. So it was like capturing data, parsing data, and then analyzing data. And then obviously I needed to have a sort of an interface to request the sort of information I needed. And it was kind of a fun, sort of application that I built in my free time working from home. And it was quite funny because I literally got to this point where all these applications, all these small services were written in Java because I was going to just have a Java application deployed into my VM. And I ran into a lot of problems. Obviously, if one of these services went down, I had to kind of figure out where that error resides. And then I had to kind of scale up the entire VM instead of kind of being able to scale individual services. Because it was a monolithic application. And that gave me some motivations to kind of learn about microservices and containers, even though I knew that already, but I wanted to kind of try it out on different public cloud platforms like AWS, Kubernetes and AWS services, and like the Azure Kubernetes services, so AKS, IKS, IBM Kubernetes services, and different ones. So for that, I had to kind of convert my application into a cloud-native application, and that's where I'm going to talk about it. So what I did, I broke down those services into individual services based on their functionalities. So a data parser, a data capture, so each one of them were completely unique, and I containerized them with all their dependencies and libraries. This way, I made them sort of capable of running on any cloud. So they were like cloud native, and I'm going to talk about them. And that gave me the option to even take advantage of different programming languages and frameworks, because I could easily just package them with their dependencies and libraries and just deploy them anywhere I wanted. I didn't have to do everything in Java. Even though Java is amazing, I've been a Java developer for 20 plus years, but that gave me the option to take advantage of a broader sort of ecosystem. And the last one was actually I wanted to kind of look for some patterns in COVID-19 data. When I could see like in some regions, suddenly it was like kind of growing rapidly, and some other regions it was kind of slowing down. I wanted to kind of, apply some little minimal machine learning to figure out what's actually going on, even though it made no sense actually back then, but I just wanted to try it out. So that allowed me to kind of take advantage of some of those amazing Python libraries out there, and I managed to actually get the Python service without even making any changes, and just containerize it and put it on my cloud. And this way, I had a very cloud-native sort of environment for my application. So I ended up kind of making this tutorial. It's a full tutorial from all the background, basic information about microservices, to Docker, how to containerize it, and then Kubernetes. And I even went further to code-ready containers and, an OpenShift, basically, environment to, CI/CD using Tekton. It was about 40 hours of video on IBM Developer Portal. That's where I worked back at IBM. And it was great, because at some point on IBM Developer Portal, it kind of turned into a very popular tutorial. And I've got it on my GitHub now, with all the videos on YouTube. So if you're interested, you can actually go in there. It's about 200 slides in one page with all the videos. So I'm hoping that you find it useful, because I've had so many people reaching out to me saying like, wow, this was great to have everything in one page. So again, some of this information is not like up to date, but it's going to be useful, hopefully. So the process that I just explained to you, by basically the application that I wrote in Java, and then I broke it down into multiple microservices, and then containerized them, and then orchestrate them, which I'm going to talk about it later using Kubernetes. That process was this cloud native, kind of converting my application, my monolithic application, into cloud native. And you may wonder, so what is cloud native? So let me start by asking this question. How can we design an application that can be updated continually without kind of downtime, and different teams can easily just update different individual microservices based on on their own timeline, and applications can be migrated from one cloud platform to another. Again, as I said, I wanted to build an application that I could run it on IBM Kubernetes services, or take it to Azure Kubernetes services, or EKS on AWS. And I wanted to have that ability. And by converting my application into cloud native, I basically became capable of doing that. So cloud native is about how an application is built rather than where the application is, resides. So when you design a cloud native application, you always just focus on the application rather than where it's going to reside. So in simple terms, applications must be built, delivered, and operated in a way that they are not hardwired to any infrastructure. And this way, your application becomes cloud native. So the process that I described to you, packaging all the dependencies and libraries into containers, that basically gives you that ability. But then obviously, the bigger question is how can you actually orchestrate all those microservices? Let's say, for this application that I described to you, it was a simple application with 6 or 7 different microservices. Some of the applications that we've got in financial services, they could have over 200 microservices, 200 containers. And again, I'm even talking about medium applications. So that takes some kind of, if you want to do that manually, it's obviously impossible. So you need to have that sort of automation in the background. And there are so many solutions for that. But we are going to focus on that. But then, obviously, you might say, microservices and cloud native, how are they related? So microservices architecture is actually the building block and the most essential ingredient of cloud native. So if you want to take advantage of cloud native, you need to break down your application into microservices in order to make them cloud native. So that's the first sort of step. And cloud native application basically consists of discrete, reusable components known as microservices. So that's the relationship between cloud native and microservices. And this is an example that I've used in my talks. So on the right-hand side, we've got this monolithic application. If you look at this bit, then it's going to be left-hand side. We've got this monolithic application for an online store. So for this online store, your inventory, your recommendation services, your billing, even your, let's say, your basket, everything basically, they're all packaged together as one entity, one application. Let's say you hit the Christmas time and you've got massive number of users coming to your website. What happens is sometimes people are just looking at your catalog services. They're not going all the way to the billing. They're not going all the way to the payment services. So you need to be able to scale up your catalog services because so many users are just viewing items in your online shop. In the past, with monolithic applications, you had to, the only solution was to scale up your entire VM in order to make that catalog services basically scalable enough for, let's say, instead of 1,000, 1 million customers basically viewing your website. Nowadays, with this sort of approach that you can see on the right-hand side, when you break down your application into multiple microservices based on their functionalities, you can actually just scale that catalog service instead of scaling the entire stack. This is one of the biggest advantages of microservices. The second one, if you want to have teams to work on their own timeline, you don't have to have everyone working together at the same time. So let's say your billing service basically goes down, and you want a team in charge of the billing service to look it up and repair or fix the error. In the past, if your service was all bundled together as one entity, as monolithic application, you had to have the entire sort of team kind of working together to fix that problem. Nowadays, you can just work with your billing services team and say, hey, you go take care of that problem and fix it. And obviously, as you can see, your entire application it's not going to become unresponsive. So you're still going to have that catalog service working for your customers until the billing service is going to be fixed by the relevant team. And that's another important advantage of that. And one of the things that I mentioned earlier about taking advantage of a diverse technology stack. So different teams can use different frameworks, different programming languages, different databases. That gives you that advantage as well. So this is the sort of advantages you get by moving from monolithic applications to microservices. And as you can see, by breaking down your application based on their functionalities, those services, you make these individual services that they can communicate with messages and HTTP, and that's basically the sort of the very basic sort of idea behind microservices. And again, they are individually deployable, maintainable, and those are some of the advantages. So in the past, what happened was, and again, nowadays with a lot of monolithic applications, it was really hard to find the errors. So there was always this sort of battle between the operation engineers and developers. They're kind of blaming each other for the problem. But nowadays, with microservices, you actually have higher sort of autonomy, and sort of it's easier to find out where the problem resides. And there's higher agility as well between the teams. So teams can work in more agile way because they're not depending on each other, and different services are maintainable and deployable on their timeline. And those are some of the problems that existed in the past with monolithic applications. So let's go back to our microservices. So we've got this monolithic application, and we basically break it down into individual microservices, and they can basically be written and deployed in different programming languages. And that gives us a number of advantages as a summary. So the first one is services can evolve on different timelines, as I mentioned. And then services can be deployed separately. You can choose your technology stack according to what basically fits the purpose. And then you can scale your individual services dynamically. That was the first one that I mentioned. But the most important one, again, from site reliability engineering SRE, if a single microservice fails, then the overall application remains functional. And that's quite important. So we go back to our application. Let's say we've got a number of microservices for our online shop, and then we containerize them with Docker, let's say in this case. And this way we've got all the libraries and dependencies packaged. So each one of these services can be deployed even on different cloud platforms. So for the containerization part, if you are not familiar with containers, they're just executable units of software in which the application is packaged with all the libraries and dependencies, as I mentioned. And this way, because we do it in a common way, they can be run anywhere, whether it's on a desktop, traditional cloud, you name it. And Docker Container Image basically is just a lightweight, standalone, executable package of software that includes everything. And Docker has just become the sort of de facto standard for containerizing. Obviously, with some of the limitations, recently people are moving to different sort of tools like Podman and Rancher's Desktop and different ones. But again, Docker is sort of the simplest way to do that. So to containerize with Docker, first we need to create our Docker file. And it's quite simple. So to do that, you just need to craft your Docker file with all the necessary information about their dependencies, the environment. Very simple. So when you have your, let's say, Java application or Python application, you go into Docker. And by using these commands, you can easily just turn your app into a container. And this way, you can run it on any cloud. And just a quick information about the Docker image. It's very simple. You can just base it on different sort of images available, and then some information about the environment and how it's going to be run. And again, you can find full information about this on the Docker website. It's very, very simple. But then, as I said earlier, let's say we've got a very large number of microservices and containers. How are we going to orchestrate that? Each one of them, let's say if you're going to update some of them and some of the other ones are dependent on the other ones becoming sort of, getting updated. So for that, you need to have an orchestrator. And that's basically where Kubernetes comes into play. So Kubernetes is an open source system for automating deployment, scaling, and managing containers application. So it basically helps you to recover from failure, scale individual microservices, scale them on demand, and also make updates to the microservices without causing interruption. Those are some of the great things that Kubernetes does. And just to give you an idea, a multi-container application must run on a multi-host environment in order to eliminate that single point of failure. So if one host went down, you want to be able to push and move all the workload to another host. And that's something that Kubernetes does very well. The other one, we need to be able to create new instances of our individual microservices, like the example that I gave earlier. Let's say our catalog services is getting hit by many users, and you want to be able to scale that automatically without you actually taking any actions. Kubernetes is going to come into play and make sure that that individual microservice is getting scaled up. And that's basically what Kubernetes does. So let's say you want to update one of your microservices, and we are adding a new service, a new feature to your mix. And that's basically what Kubernetes is going to do. It will schedule new deployment and create new instances of our containers with zero downtime. So it will automatically take actions to make that happen. And then Kubernetes scales and manages our containers according to the available underlying resources. And that's another thing that it kind of, automation helps you a lot and gives you a lot of advantages. And then the last one is Kubernetes basically checks all the containers to make sure they're all up and running. There's no problem, there's no error. And if there's any problem, it will basically take actions to reinstate or just basically reset the containers. And again, all this will happen automatically in the background without you taking any actions. Whereas in the past, that wasn't possible. You had to actually look at all these sort of functions happening accordingly. So those are some of the great features of Kubernetes that does it automatically. But again, you may wonder, how can we actually make that happen? So earlier, I told you about containerizing your microservices. And now, I'm going to show you how you can actually do that with Kubernetes in a few commands. But before that, just for you to understand how those functionalities are going to happen, this is what Kubernetes basically does. We state what we desire about our application, so the number of replicas, how you want the application to be scaled, when the updates need to happen, so we define that. And then Kubernetes basically keeps working to make sure that the desired state and the actual state, they match. So there's always this sort of reconciliation between the desired and the actual state. And that's basically one of the beauties of Kubernetes, because as I will go into more details later, you will see that happening, using controllers in the background even. It's not just about your applications. You can actually create operators to run things in the background in your cluster. So this is basically what Kubernetes does. It observes the actual state continually and will keep adjusting and readjusting to make sure that those states are identical. Now, to understand exactly what Kubernetes does. So we broke down our application into microservices. We containerized them with Docker. And then what would happen next is deploying each Docker container with Kubernetes will spin up a pod with the Docker container in there. And based on the deployment scenario and the load, each pod basically gets replicated. Those are the instances that I mentioned earlier. So some of them gets replicated 3 times or 100 times. It depends on the demand. And obviously what we desire from our application. And then we basically create a deployment. That was the first layer. The second one, creating replicas. You will see the commands in the next slide. And then we basically create services for them to be able to communicate with each other. So all these containers are now going to be communicating with each other. And then the next step is to expose that application, to make that available outside of your cluster. So people can access your application through World Wide Web. That's basically what will happen within that Kubernetes cluster. And if you wonder how that's going to happen, as simple as this, 4 or 5 commands. It's very simple. You basically create a deployment, as you have seen in the previous slide, and then you expose your application, and that's basically, that makes your application available to the outside world, and then your application is accessible. And obviously, you can scale different deployments. You can roll back and roll out and do different functionalities with it. But the simplest way is just to deploy your image and then expose it. That's all it takes. And in case you wonder about batch operations, so you don't have to do everything like on a command line basis. So you don't have to do everything like that. You can just define your operation in a YAML file and just apply that YAML file, and everything will happen automatically. But then, as you had seen in the previous slide, and you can see here, we've got this kube control, kubectl, or kubectl, people call it differently. That's basically your magic word to communicate and interact with your Kubernetes cluster. In case you wonder how that happens in the background, under the hood within Kubernetes environment, so we use kube control to interact with Kubernetes cluster, and then the Kubernetes cluster lets us control Kubernetes cluster and resources basically by communicating with the API server. So that's within your master node. And then master node processes our request through the API server and runs a scheduler service that automates when and where the containers are deployed based on our declaration. And then each worker node includes a Docker and a software agent called kubelet that receives and executes order from the master node. And then the kubelet basically spins up new pods. Those are the instances that you saw in the previous slide. To direct basically, and then to expose our application to the external network, our master node creates a service to direct traffic to our pods through worker nodes kube proxy components. And that's basically all happens within Kubernetes cluster for your application to become accessible on the web. Very simple. 5 commands, 4 commands, you can make your application accessible. But then to go back to that previous slide that I talked about, that control, that sort of observation. So that's a very simple concept, but again, very important. So it's just like that desired state and the actual state and that sort of reconciliation that needs to happen. That's basically through the controllers. And that's very important because if you, let's say, define an application with, let's say, 3 replicas, and then one of them basically goes down, immediately Kubernetes takes actions to reinstate that. And it will basically come back on because you have defined your desired number of replicas as 3 replicas, and it will basically happen. It will always make sure that there are 3 instances of your application running. Or let's say you update your application to version 4. Immediately, Kubernetes takes action without downtime because it keeps some of the version 3 still up and running by bringing in the version 4 gradually into the play. And that's actually quite important, again. Very important for those who used to use VMs and you had to make your application inaccessible for a long time. This will happen automatically. You deploy your new version, and it will basically come into play. But again, you may wonder about more complex applications like databases, like queues, message queues, and all that, because in those applications, the pods, when one pod goes down, the other pods comes up like in a stateless application because they're identical. So immediately you can actually spin up another pod. Whereas in a stateful application, they're not each pod. The pods are not identical. So the last pod might not be completely updated and exactly identical to the other pods. So when one goes down, you need to make sure that the last one that you're going to, the new one that you're going to spin up actually matches the one with the most updated version. And this way, basically, Kubernetes takes care of that by a number of operations to make sure that always the latest version gets replicated. And for that, you need to use a stateful set, set basically to make that happen. But then there is another concept here that if you want to move from one cluster to another or put all your libraries and dependencies into your cluster, you can use Helm to make that happen. So Helm is a package manager that allows developers and operation engineers to easily package, install, and reconfigure. So this way you can actually take your configuration from one cluster to another for your application. And again, I don't want to talk much about Helm, but think of it as YAML files that will basically work together in like a manifest combined into a single package. And again, we call them Helm charts that kind of can be advertised to your Kubernetes cluster and basically tells Kubernetes what sort of deployment, CRDs, and all those things you expect from your Kubernetes. Again, I don't want to go much into details, but the important point here is Helm's primary focus is on the day one operation. And then it basically uses that to make sure that your cluster is always up and running and it's got all the necessary configuration that you desire. But the problem with Helms is, there are cases where application, complex requirements, they can't actually be expressed in YAML, and some of them in a hierarchical manner, you can't actually make that happen. And if you have a very complex operation or a knowledge for your application, you can't actually embed that into YAML. And the problems are obviously like this. Persistent is not completely or properly handled, and errors are actually quite hard to trace. So what you can do here, you can actually take advantage of operators. And again, operators are the native way for Kubernetes to handle all those underlying operations. And again, I'm going to talk about operators shortly, but think of Helm as your day one operation and the operators as day two management for your applications, that you can actually embed your application knowledge into operators and put it into a cluster rather than running it as a new application in Kubernetes. So operator is a custom controller that understands how to manage a specific application or a service. And it's a powerful concept that enables you to automate the management of complex and stateful applications in Kubernetes. The main benefit of Kubernetes operators are automation and standardizing, some of the application requirements into your application, into your operator, into your cluster. So those operations that I mentioned earlier, they were using the default resources. So deployment is a default resource in Kubernetes. Creating a pod is a default resource. A service, when we expose our service, those are default resources in Kubernetes. But Kubernetes, it can be easily extended, the APIs in Kubernetes, so you can actually have custom resources. So whatever operation you want to define, you can easily just extend the Kubernetes APIs and create your own resources. And custom resources are extensions to Kubernetes APIs, and you can easily embed your application knowledge into those custom resources. And basically, custom resources can be used to represent new types of workload, such as databases, caches, or message queues. And this way, you basically create more capabilities within your Kubernetes cluster. So let's say you have a database application, and you want to define a custom resource that represents that database instance specifically. So you basically create your operator and embed all that knowledge, and the controller is going to be there just to make sure that always your application is going to behave in the way that you desire within the cluster. And then your other application can easily take advantage of this operator because it's a new custom resource with whatever name you basically define, as I will mention in the next slide. And this way, your Kubernetes cluster can be identical when you apply that operator into different clusters. So custom resources may require additional configuration and setup, such as creating a new controller to manage the custom resources, while default resources can be used without any additional configuration in most cases. So an operator is essentially a software program that interacts with Kubernetes API to create, configure, and manage custom resources. So now you've got your custom resources, but also you need to have a controller attached to it just to make sure that your desired state and the actual state, they match. That's another important point, because that happens with our custom, with the default resources, and you want the same behavior for your custom resources. And to do that, you need to define your custom resources through custom resource definitions, or CRD. And that's a feature in Kubernetes that allows you to define custom resources and their schema. And this means that you can define your own Kubernetes resources that represent specific objects or applications that are not already provided by Kubernetes. And this way, again, using YAML, you can easily define your custom resources, and you can name it in any way you want, and you can actually create a hierarchical manner for your custom resources. So one custom resource can easily extend another one, and this way you can actually put it in different environment or namespaces for different set of users for different functionalities. So let's say, CRDs, custom resource definitions, can be namespace or cluster scoped. So this way, your deployment, testing, staging, and production can have different versions of your custom resources while they're basically extending the same set of custom resource definitions. That's quite important. So for your testing, you could have a different set of custom resources defined for, with different RBACs, with different access management and controls. And this way gives you a lot of advantages. You don't have to do everything in one cluster. And then it's actually good for A/B testing, for blue-green deployment. Those are some of the advantages you can actually get from custom resources. And again, as I said, hierarchical relationship, they are very important because it gives you a lot of flexibility. And the last one, obviously, I want to talk about observability. So again, no matter how good you've designed your application and where you run it, again, it could be full of bugs, it could be full of errors. And again, for compliance and standards, you want to make sure, again, in financial services and some of the critical areas, you want to make sure that your applications are bug-free. And for that, you obviously need to have observability because you want to be able to find it first and handle it properly, and that needs to give you that granular sort of monitoring in place. But then you obviously need that sort of, we call it the four signals, golden signals: latency, traffic, saturation, and error. So whatever you do, you want to make sure that you've got full information about these four signals. And obviously, there are so many open source tools out there, and even commercial tools. But then you want to have that sort of ability to have the pillars of observability: traces, metrics, and logs. Those are the important information you want to collect from your application. Grafana and Prometheus together, basically, they give you that sort of ability. And again, they're fully open source. And I will mention a few details about them again. We're running out of time. So, but those are the important pillars of observability. And again, Kubernetes can easily provide you with all the logs, traces, and metrics you need. But then obviously there are differences. For monitoring, you're always looking for error, traffic, latency. Those are the 4 signals that I mentioned, saturation. And then observability is about logs, metrics, and traces. So those 2 together gives you that sort of flexibility and capability to monitor application and recover in case you need to. Observability in Kubernetes, you can do it differently, but you can actually do it using agent-based observability. So deploy monitoring agents on each node and pod in your cluster, and then agents collect metrics, logs, and any data from the components. And then traditional approach to Kubernetes observability basically is to get those metrics APIs and make sure that you collect the data when needed. And there are new ways, in the third approach, using agent-based Kubernetes observability with eBPF. And that's basically getting observability data using extended Barclay packet filter to collect traces. It's not that complex, but again, it's not that common, but it's becoming quite popular to have your, to pair that with some of the data sources and tools. That gives you that sort of flexibility. Whereas with the metric API, you have that native Kubernetes features that exposes data about the resources, usage for pods, nodes, and we can just name, as the name implies, you can actually generate metrics only, but not logs and traces. With that, the last part is basically best practices for observability in Kubernetes. You need to define your metrics, automate monitoring, integration with CI/CD. Those are the important lessons that I have learned throughout my career, and for that, always identify the key metrics, and make sure that your automated monitoring is always there to detect and respond. And again, using the operators, you can make that happen. You can actually embed that into your cluster rather than deploying an application to look for those. And in integration with CI/CD, it gives you that sort of ability for the validation and also for testing and checking, which I think most of the critical services need that to happen. And the last one, popular monitoring tools, Prometheus, Grafana, Datadog, they're out there. And again, there are so many others, even like Instana, AppD, there's so many. But again, those are the great ones for cloud-native applications, and they're open source. But Datadog, again, is different. It's not that open source. You need to have the commercial one. But they give you that sort of data visualization for taking actions when needed, and they can be easily embedded into Kubernetes cluster, even OpenShift, for checking your application continually. With that, thank you very much for joining my talk today. I hope you have found it useful, and I'm ready for any questions you have. Yes.
You had said earlier there's a limitation with Docker, and everyone's trying to move away from there. What are those limitations?
Limitations in terms of their changes to their commercial licenses and developer licenses. I think it's more than, if your organization is more than 250 people, I don't remember exactly. So I think for that you need to get a commercial license, and that kind of limits your sort of flexibility, which in the past you could easily just use it free of charge. But nowadays, if it's more than 250 people in your organization, you need to get a commercial license. As far as I know. That's why many people are moving away from Docker, those who don't want to pay.
Just a personal thing, do you think that's fair?
You have to look at it from their perspective. I think many people were using Docker free of charge and not paying, so maybe at some point they decided to do something about it, which is not a bad thing. But the features they had was amazing for developers in terms of simplicity, and it was like a de facto sort of tool for everyone.